We're continuing on with this introduction to curvature, and the concept of curvature has a formal definition and a formula to calculate it, but I was really more interested in looking at three possibilities. And so we proved already that the curvature of a line is 0. It's not supposed to curve. The formula agrees with that. The next thing I want to prove is that for a circle, the curvature is always the same. Never changes. Constants never change. And then we'll do the parabola last. So this is a circle. It happens to look something like this. If we were to create x and y axes, it would have a radius of 5. It would start here and it would go in this direction if we plotted the points. Those are all concepts from the early part of the chapter. So to find the curvature, we need the velocity cross product with acceleration, and that's a vector we find the magnitude of, divided by the magnitude of velocity cubed. So let's just go through and find the components of this, and let's just run this formula through. I'm going to prove to you that the curvature is a constant for the circle. So, velocity vector, -5 sine t, comma, 5 cosine t. The magnitude of that vector, that would be 25 sine squared t. I'm writing it out. You've seen me sort of cheat this in a previous segment. And plus 25 cosine squared t. This is going to be the square root of 25, which is 5. They don't always come out to be nice constants, but that's not too bad. And I do need acceleration. And acceleration is, let's see here, -5 cosine t, comma, -5 sine t. So I need to do the cross product of velocity and acceleration and then find the magnitude of that afterwards. Now watch this. I don't need that part anymore. Watch this. When we do cross product, I, j, k, let's see here, velocity, -5 sine t. Can you see our problem yet? 5 cosine t. There's no third component. Well, that's right. There's no third component. It's 0. And similar for acceleration, -5 cosine t, -5 sine t. Third component, also 0. And if you start to work through this cross product calculation, whatever method you choose, you're going to find out something interesting about this. Well, I get to define interesting in my classroom. Maybe it's not as interesting to you outside of my classroom. But you're going to get zeros for the I component and zeros for the j component. You only have a value in the k component. You're going to get 25 sine squared t minus a -25, which would be like adding, cosine squared t. And the last time I checked, that's equal to 0, 0, 25. Well, if curvature is the magnitude of that vector over the magnitude of velocity cubed, the magnitude of this vector is just 25. And the magnitude of velocity was 5 cubed. That's 5 squared. This is just 1/5. I was so excited that I didn't slow down and savor the moment. This is a constant, folks. There's no variables in it. It's always 1/5. More importantly, for some people, 5 was the radius and 1/5 is the curvature. In general, for a circle, the curvature will be 1 over its radius. We won't prove that right now. I'm going to write radius here so you don't confuse it with the other r that we have. So there it is. Circles have a constant curvature. One more to go. Remember, you do have a pause button. Parabola. It would look like this if we started here and went that way. We need the velocity vector. Let's see, 1, 2t. We will need magnitude of velocity. 1 plus 4t squared in the root. And I will need acceleration. Slow down, slow down. Second derivative of 1, that's 0, and that's going to be 2. So before we go and actually find a curvature, let's do the cross product. Let's see, I, j, k, 1, 2t. The third component is 0 in both cases. 0, 2, 0. And if you start to evaluate this, which by now you've done quite a few times, so if I'm going too fast, pause. Do it yourself, then see if my result matches yours. You try first, then come match to this. That's going to be 0, and that's going to be 0. And this is going to be 2 minus 0. I mean, that's just 0, 0, 2. So curvature is the magnitude of the vector I just found over the magnitude of the velocity cubed. Well, the magnitude of this vector is just 2. And the magnitude of velocity, 1 plus 4t squared in the root. See that letter T? What do we call that again? Oh yeah, it's variable. That means the curvature of the parabola is different at different places. So, question. For fun, of course. Where's its curvature largest? What value of t makes this fraction the biggest possible value? I'll drop it at the end, but I want you to think about that. And then finally, what if t were to go towards infinity? What if t gets large? Let me answer those, and we'll call it quits for this segment. The numerator never changes. If the denominator gets bigger, the fraction will get smaller. So your curvature will be largest when t is 0, which happens to be at the vertex. And what if t goes to infinity? I think you will find that this fraction approaches 0 as t goes to infinity, and that's simply just saying that the parabola gets straighter and straighter the farther out that you go. Fascinating stuff, this curvature. Until next time, we'll see you later.